goes south because I don't trust it. uh, I'll post this recording on YouTube and post a link on the let's see, go back to Blackboard here. I'll show you where the link is. And since I made all the videos public last night, um, you should be able to just click on the link. Let's see. By the way, if you've had trouble getting into the UGA lectures, the best thing to do is click on this link right here and click on that pink bell up in the right-hand corner. That'll take you right to it. But now that I've done that, I have to go back to my courses. Kicks you out of your course. CNC Mill. And I'll check for questions occasionally, particularly after each thing we talk about. I've got this Word document that is kind of explaining the lab thing that's going to be the week after class is actually over. And pretty much taking the first 9 people really, because there can only be 10. And you're welcome to do this. I'm going to be down there on Thursday the 14th and Saturday the 16th during these times. And I'm going to post this as an announcement. But they will be requiring you to wear a mask. So all the information about that will be in here. I just got this last night. They're kind of flying by the seat of their pants on this. So most of this terminology was provided in a letter to me. And I changed a few key things about it being totally voluntary and it doesn't go towards your grade. Some classes are different because they have different requirements. But I'll post this after class tonight, and also my daughter has a recital. It will be after that. So a virtual recital, because I originally wasn't planning on being here tonight, but since her recital got canceled, do I need to finish Sim 151? No internship. I don't think so. If that is the case, if they tell you you have to, I think you can start lathe, and worst case scenario, I can submit a class override for you if they say that you can't for some reason. Particularly, I think they like you to have manual lathe first, but I've seen people take manual lathe and CNC lathe at the same time. So, but I will give you an override to get into CNC lathe if you need one. If they tell you you need a certain class, I can just send an email down to class override, and they'll get you in if you want. So that's easy. Since you've had CNC Mill, yeah. So I'm going to just pop the book open here, and then I'll, again, post that letter tonight. What I need is for you to confirm that you want to do it. And then I send your name to the dean the division chair. And they just want to know who's planning on being there, because they have to probably adhere to some pretty strict guidelines about how many people we're going to have. So I'm going to say you can attend the Saturday and the Thursday class or lab if you want, unless I get more than 9 people, then it'll just be the night that you would normally have class. So just to make it fair, I doubt that more than half of you will want to do it, because there really truly is no points value going towards that. So all right, I'm just going to open up everything that you need to know for the final exam is in the programming workbook. And the homework has really been structured around the final exam. And so just kind of go through here. You won't need to have your G codes memorized, other than filling in the blanks, just like the homework. In other words, it's going to be open book, open note, obviously, because why wouldn't it be? I'm not really putting a timer on it, but it would be great for you to turn it in at least by 10 o'clock on Thursday. So we'll meet here next Thursday, and then I'll introduce the final exam and turn it on, and you'll be able to work on it. I'll be available for questions, but I'm not going to be like sitting here online, because that'd be dumb. So y'all can text me. I've got my cell phone right here, you know. During the final exam, it's a comprehensive, like if you have a question about some verbiage or anything like that, how things are written. So this Haas manual is really well written for June 2006 that it really is, because it's like quite old at this point, kind of like I feel right now. So you might just kind of go through and review some of this coordinate system stuff if you need to. I haven't had a lot of required reading. For me, I always learn better by doing things, and I'm kind of a screw it up yourselfer. I have to mess it up once or twice and then go back and finally do it the right way, and then I tend to not forget. So this is real basic review here. The machine home is really, they're making it look like it's in the center of the circle, but machine home is over to the far right back. So it makes it a little easier to remember than this whole quadrant business. Anything, if I'm looking at the machine table and it's in front of me like this, anything that moves away from home 0 is going to be a minus direction. So this direction is X minus. This direction is Y minus. By the way, I'm assuming everyone can see the workbook as I'm going through it. Yeah? Yeah. Okay, good deal. So everything from machine home and Y going in this direction is going to be Y minus. And anything from machine home and Z, so this is a really great picture. If you're having trouble with your X, Y, and Z plus or minus which direction, this would be a great picture to refer to, because this is machine home. Anything moving away from machine home is a minus direction, Y minus, X minus, just like the arrows point, except this is pointing towards Z plus, which is confusing. So that's just that simple. The difference between absolute and incremental is as simple. I think the number line is kind of confusing, but it's always kind of difficult to explain things without using gestures. But absolute, again, is from wherever you position your part 0. Remember, we take our edge finder, position usually the fixed jaw of the vise in the left of the part or the center of the part in X and Y. And then that we would make that our part home with G54 through G59. But this position, my mouse wheel's acting up again. I really need to get a new one. I use my arrows. The machine position direction doesn't change. X minus is still, we're going way back to the first semester. X minus is still this direction. Y minus is still this direction. So if you remember which way minus is, then you don't have to worry about which way plus is so much. The G90 and G91, absolute, incremental. G91 is from one point to the next. Jeremiah had a good point. On the drill cycle homework, he did his in incremental. So it was like G91, Y minus, whatever. You can actually use an L value with that. If you've got 10 holes and they're all an inch apart in X, you can say G91, X 1.0, L 9, because your first hole would be drilled. And it would drill 10 holes. It's really handy. I had a part at Procon that had like 1,100 holes in it. No kidding, 1,100 holes. I just masked it and selected all the holes with Mastercam, but if you had to program that manually, it would be easier and take a lot less programming space to use an L command Again, that's not going to be on the final. There I go, rabbit trailing. I was like, I'm just going to talk about stuff that's on the final, and I don't know if I can do that. I'm going to try. So let's see. G91 is from one point to the next. So these are explained really well here. Does anyone have any questions about G90 and G91? That's probably going to be on the final in the form of, filling in the blank for a program. Also, if you're not comfortable with asking questions in the UJA format or typing in, or you don't want to mess with typing, you can ask me questions throughout the week. Now, I will say if you ask me questions between Wednesday and Thursday, I probably won't get back with you till Thursday after class. So because Thursday is kind of my slingshot, because I go straight from work to pretty much home to school to same deal. So the positioning exercise, I mean, if you're having struggles with X plus and minus, or Y plus and minus, you might just take a little time to review some of this stuff, and you might be surprised at how sometimes things that seem difficult at first are a lot easier when you look at it the second or third time. So this is your basic programming format in English language. I don't spend a lot of time with this, but it's basically, if you were going to speak a toolpath, this is how it would go. So the format of the program on the final is pretty well spelled out for you. If you're in the advanced lathe class, you won't have that luxury. You're just going to get a drawing and then write the program from there. So a lot of this is review. It doesn't really apply to any geometry, so kind of skip over that. These are good things to know. I'm not going to spend a lot of time on that. So the program's first couple of lines, and I had some of you guys sort of struggle with this. This almost never changes, other than where you're going to position X and Y, how fast are you going to turn the spindle based on your tool, and what is your tool number, because H1 and T1 always have to match in your program. M8, M3, these are all turning on your spindle, turning on your coolant for M8. Good idea to tell it G90. Reason is because a lot of times before this line, you'll be an incremental taking Z home. And the last thing you want to do is leave this thing in incremental when you're repositioning your X and Y, because it's going to just move it from where it was to to these values here, and it's probably not going to be where you want it. It's usually good to stay in absolute when possible. Seen a lot of tragic things happen by leaving the machine in incremental. So G43, we're just these, you see these codes and these lines together, and they're usually paired together for a reason. Because your G43 H1 is going to run over and fetch the length offset for whatever tools in your spindle, because rarely do you want to run a part that just has one tool, and so you don't want to have to tell it different Z values each time you change your tool, so that offset removes the need to do any of that. So anything that's in parentheses will be ignored by the control. So it's a good thing to add comments about what your stock size is, anything, what the tool is. Normally I'll put what is my tool, what are my setup points. If you've done we've done a fair amount of programming with that same format over and over and over. There's some rules about G codes that you really don't need to know. You might want to keep in mind where this list of G codes is, because you're free to use the book. um, for the final. So no more memorization. And my experience is that most past classes, I think this is my 5th time with this class, maybe 6, but it usually probably takes more than an hour on average to do the final. 1 to 2 hours. And if for some reason you can't do the final next Thursday, you might just drop me a line. I'll work something out with you. So these are your machine defaults. When you turn the machine on, this is what the machine is set to. So here's pretty much your safe startup line, with the exception of G64 and 69. We didn't really learn those. Exact stop is a thing that I believe is used if you have a problem with the machine overrunning. We run into that problem a lot with some of these flow toolpaths that just have thousands of lines of code and just as tons of processing. Sometimes the machine will get ahead of itself and it'll miss a point. And so the exact stop forces it to stop after every block. Just a little 401. That's not on the test. All your M codes and G codes are at the front of the book here. So you might, if you have a book, you might dog ear it, or you might go through and write down where some of these, if you got a pen and paper, you might jot some of these page numbers down. What's more important is probably the page number that's right here, because you can actually search around. And you can have the book open in multiple places too if you want on your computer. So there's just a couple options. Like you can have your M codes pulled up on one tab, G codes pulled up on another. Some of these M codes we never used. And I will say for the most part, the M codes that we're using, clear up to M9 and M30, these are all really standard as far as machines that I program use these same codes for M codes. You get into these like M11 and M10 are pretty standard too, but like chip auger stop and things like that, that's going to be really machine specific. So you always want to be able to have your manual handy. Oh, we got a late comer. Program structure. This is you can access some of these program examples when you're doing your final if you are having trouble or just need an example to go by. One thing we didn't cover is these little slash marks in front of the X and Y position. That is a block delete sign. And anything that has a slash mark in front of it will be ignored by the control if you push the block delete button on the front of the control panel. That's also super typical of most controls that I've worked with, which would pretty much include, at this point, Heidenhain, Morisiki, which is Fanuc, Okuma, and that's about it. I've done it a little bit with Herco, enough to not like them. It's kind of back to that. You don't like things that you're not familiar with because it takes you longer to do stuff. Don't ever, shy away from trying to learn a new control, because you might be find yourself the only person in the shop that knows how to run that machine, and it'll make you more valuable. I've heard people tell me stories that, I got this old Mazak or something over in the corner and no one would mess with it. And then I went over and started using it, and now they're relying on me when they want something done on that machine. So got to be kind of bold out there. But the reason they would use a block delete with this X and Y position is maybe you have a part that just has one hole in it, 2 holes, And it sometimes has two other holes. So rather than have two completely different programs, you can put a block delete in front of that value. And if you're running one part, because I mean, who here has not had a part family, a group of parts that would be in a part family? No, I'm not going to give you a drawing that you have to program. It's going to be fill in the blank, a lot like the homework. So that won't come unless you take my advanced classes, which I think a lot of you could just write a program from top to bottom if I handed you a drawing, but that's not really the scope of the class. So the advanced is different. One thing I do different than I think Dave Grady has a machining final and a written final. I've always shied away from that because I don't want people to be rushing around to try to get a part done and crash the machine. You know what I mean? So it just seems like a way more relaxed final exam, and nothing gets broken that way. I do the same thing in the advanced class. There's no real, got to hurry up and get this part cut final. None of this is really relevant. Well, I wouldn't say relevant, but it's not going to be something you're going to be quizzed over on the test. There's no I and J on the test, which some of you will be really happy about. Any kind of circular contours that you have to program are all done with the R value, and we'll review that as soon as we get to it. These are just kind of describing the different variables that you'll run into. So it wouldn't, hurt to thumb through this week, especially closer to next Thursday, and at least have a good idea where stuff is in the book. Rapid positioning, a couple examples of absolute and incremental programming. Linear interpolation, so G0 and G1. Most of you guys get that pretty good. So here's a good example of a contour. Now on the final, when you see your contour that you're in charge of programming, by the way, if you take the NIMS CNC final or written, it's a lot like this, where it would ask you, it might leave a couple things blank, and then you would have to fill in what the programming is on it. But pay careful attention to where your X and Y 0 is, because that is going to be, that's my daughter singing with her teacher. Kind of distracts me. So again, with cutter compensation, anytime you see this G41 or G42, you're going to program the exact geometry. And if you're struggling with this, I would just say it would help a lot to just circle each exact point that you're going to be programming on your contour. So in other words, this would have 1, 2, 3, 4 points. And think of it like an Etch-a-Sketch, where you're going to move Y up, and you're going to move X and Y, and then X. So this is a Y plus move from here to here. Y plus X plus move because you're getting closer to home. And another X plus move because you're getting closer to home. So think of your machine home being over here. And any movement away from home is in the minus direction, and any movement towards home is in the plus direction. Another thing that I'm going to count off on the final is if you leave out your decimal points. So it's probably the number one thing that I see students doing is leaving out decimal points. It really makes a difference, because if you say F12 without a decimal point, it's going to think F.0012. So that's going to be a pretty substantial production delay. Why did you have to program a part from scratch in CNC lathe? Did I do in CNC lathe? Because that was, what was the final in CNC lathe? I don't remember. Yeah. Oh, yeah. That was the oh, David Gray. Yeah, that was the NIMS project more than likely. I think some people think that CNC lathe is a bit more difficult than CNC mill. There's a lot more rules with CNC lathe than there is in the mill land, especially with radiuses and diameters. But so don't get hung up on how far the cutter is away from the part, because this little G41 is the magical, hey, we're going off part geometry now. We're not going off the cutter radius anymore. So you can program like G1, G41. Remember, you always have to start away from the part. And as you're moving to X0, the cutter is theoretically vanishing to the sharp point. And once it reads that G41, everything gets programmed right to the next point. So notice this G90, absolutely go to Y 1.750, which is this exact dimension from 0. And then this is from here to here, 0.546. So it'd be, they don't give you that. You would have to trig that out because they give you the 2 inches. That's another thing that's not going to be on the final. You're not going to have to trig anything out. All the dimensions that you need, in other words, you're not going to say, okay, well, if this is 70 degrees, then this is 20 degrees, because if I had a full 90 degrees, then this would be 20 degrees. And then I'd have to know one other thing. Oh, you'd say from 1.750 minus 3.250 would give you this leg of the triangle. So with this 20 degrees and this leg of the triangle, you can figure out all 3 sides. So trigonometry is not hard, except for the fact that my biggest challenge with trigonometry has been, where do you draw the triangle? Not solving the problem, because with trig apps and everything, there's you can solve the problem just by plugging in one side and one angle. In fact, trigonometry, SOHCAHTOA is kind of obsolete for me. I knew it at one time when I was studying for all my NIMS tests and everything, but I quickly forgot it. It's not that it's hard, it's just one more thing to have to try to remember. So trig app is everywhere. Trig calculator, Symbolab. Oh, I don't think that's the one. No, that ain't it. There's trig calculators online, so even if you don't have one on your app on your phone, which is what I recommend. Where is the triangle as a trig? So here's one. Like, you can plug in any side or any angle and hit enter, and it'll fill in the blanks for you. So if angle A was 20 degrees, or no, angle A is 20 degrees, and this was 1.750 minus 3.250, 50 minus 3.250 was 1.5. I should have been able to do that in my head. And side B is 1.5. See, it just fills in everything for you. So that's where they get that 546 right here. So X is 546 because it's just part of that triangle. Because from here to here is 1.5, 20 degrees here. Solve the whole problem with a trigonometry calculator. Now there are people, like if you work at Honeywell or something, you're not going to be able to use your cell phone. But from what I understand, you do have access to computers. because they just don't want you taking pictures of stuff. So you could like, access this app from a computer or something like that. And to me, it's just easier and faster than memorizing the SOHCAHTOA, although, because you forget it really quick. Because most people say, oh yeah, SOHCAHTOA, it's, let's see. And I'm like, by the time they do that, I've already whipped out my calculator and figured out solve the triangle. So the big point is this 3.250 is exactly 3.250 from 0. 546 is exactly 546 from 0. And going to feed right over to X 2 inches exactly. So even though the cutter is on the other side of this, it knows to do that because you told it cutter radius compensation left. Part as it's moving this way, as it's moving in the Y plus direction, the cutter is to the left of the part. If it was G42, the part would be on this side. So I always think of my body being the part, and my cutter is my hand moving away from my body. So typically on G41, it's going to be clockwise movement around the outside of a feature. It's going to be counterclockwise movement if it's a pocket, and it's the opposite if it's G42. It's going to be counterclockwise on the outside of the feature and clockwise on the inside. What we want is G41, because if you think about it, as you're crawling around the outside of the cutter, the chips are coming out the back. All right. And what happens with conventional milling is if you're coming this way, the chips tend to scoop around back into the cutter. And I've seen cutters look brand new that were climb cutting, and the same cutter will look totally dull if it's conventional milling. You always get a better finish with climb milling. The only time you don't want to do this is on a manual mill. You don't want to take heavy climb cuts on a manual mill because it'll throw the part out of the vise. The machine's not designed to handle that kind of chatter. It tries to grab the part. Now with the CNC, if you have ever seen dynamic milling, it climb cuts at a really high rapid rate. It will use a feature called chip thinning, so it detects when it's going to engage a heavier cut and moves away from it. And so it just climb mills, rough climb mills all around the part, which is pretty fascinating to watch because it's usually about 100 inches a minute too. But what you will need to know for the final is, where to plug your points or your geometry. Just ignore the cutter and just think about where are my exact geometric points on the part. That's what this is programming, and that's what will cut the part exactly right. Now there are different schools of thought on this, but the style that we're doing, this is what you're looking for. So we go to X 2 inches, which is right here. The next part of the contour is down to Y0, which is Y0. And then we feed over to X0. And notice when we G40 out, we're basically telling the cutter to reappear. Now it's perfectly fine to just move over in X or Y. You don't have to move over in both. The big rule here is one direction has to be more than the radius of the cutter. So if you got a 0.5 diameter cutter, you're going to have to move. This is why they're moving 350 thousandths in X. That's 100 thousandths more than the cutter. I got shaving cream in my ear. Drives me crazy. You never realize it till you're. I got somebody calling me, but I'm not going to answer that. Doesn't look like a student. If you have a question, you can just text me. It's probably somebody trying to sell me health insurance that I don't want to buy. Anybody have that? So we need to kind of go over circular interpolation as well. That's going to be on a contour. You will be responsible for programming a contour. You'll be responsible for circle pocket milling. There's sub-program involved. And so we're just going to try to cover the finer details of those things. So circular interpolation, I and J, you're not going to have to worry about. We've explored that a little bit. Just as a reminder, it's always a source of confusion. Even with the machinists I work with that do this all the time, they just forget because they don't. I used to struggle with it too until I started teaching it every semester, you know. So when you explain it enough time, you finally remember. But it's from the start point of your cut to the center of the radius all the time. So whether it's I is always for X, J is always for Y, and K is for Z. And there are times where you will cut arcs in Z axis, and that's where we get into the G17, 18, and 19 plane selection, which again you're not going to have to worry about. But we'll have to be able to cut a 90-degree arc as part of the contour. So I think I'm pretty sure we'll run into that here pretty quick. So we're already halfway through the book. Let's see here. This is, some pretty thorough descriptions. Sometimes the descriptions are a little bit hard to understand. Now, this is an example of programming an arc without cutter comps, okay? And so we don't want to get this confused with using cutter comps on an arc because the radius changes from the actual radius, which if this is a 500 radius, by the time you added the half-inch end mill, which has another quarter-inch radius from here to here, adding those two together is going to make that a 750 thousandths radius. And so if we were manually programming this without cutter comps, that actual radius that you would program would be 750 because it's got to go another 250 to make it to the center of the cutter, which looks fairly understandable here, but when you start cutting parts of radiuses and segments of circles, and it just seems like every job I come across. Oh, I know. We're looking at this one job. I should have brought the step file home because it's a mold for a dog biscuit, right? A dog biscuit, but it's got a twist in it. In fact, let me turn on my Google Mail, Gmail here. And because I took a picture of it today, hopefully it's sunk to my phone. And you guys won't try to hack into my email, surely. And let's see, pictures, photos. Sorry. No, it's not. It didn't sink in yet. Rats. These are the big, large castings we're working on. This thing is like 4 feet long. And I was just hoping to. Oh well, I was sorry about it. You'll never get those 10 seconds back. See, does anybody have any questions right now? Okay. So anyway, this thing's a mold for a dog biscuit, but for some reason somebody decided the dog biscuit would be more appealing to animals if it had a 15-degree twist to it. So I was really wanting to show you a picture of that because it's like, that'd be a reasonably easy thing to make, except now it has a twist to it, which you'll have to put that on a 5-axis machine and use swarf tool paths and all kinds of fancy things to get it to make it. So I was like, the dog does not care, but I guess the marketers do. So anyway, what we want to look at more is the cutter. Like, ignore this example. If you're doing review, ignore this example because it's showing you how to cut this radius without cutter radius compensation. So this would be more of your example to look at where, it just gives you the points. So here again, be sure you know where your XY origin is. So they've got a G2 X minus 2.250, which is 2 inches from, this one's confusing to me. So this is 2 inches typical. I think this is actually without cutter comps. This is not using cutter comps. That's what we don't want. We want this one. No, that one still uses it, not using cutter comps. Those are both really bad examples anyway. Let's find a good one. I think the one right before the actual interpolation exercise is probably the best one for examples. That's an internal pocket. Could have sworn they had a way better example. So for an internal pocket, which I don't think you have to do an internal arc. They're a little bit more tricky. 1.250. That's a really not great example. Of course, my mouse is being ridiculous. Probably this example right here. No, they're still using non-cutter comps. Well, hopefully we'll run into a better example. I guess we could just go review the homework. If you have your homework, you can review it. It's been graded and correct. Everything's correct. Page 61 in the actual book. Okay, we'll get down to that then. Thanks, Joe. So your startup lines, all the information that you need to get through the final is in this book. You're not going to have to go from inch to metric, but if you ever did, G20 and G21. Work coordinate, just remember that G54 and G59 pretty much are the exact same thing. They're just, if you want more than one work offset. If you remember when we were down at the lab, I was saying it would be smart to make all your work offsets G59 because then no one would mess with it from week to week because they'll be using G54 or G55. Tool length compensation, that's G43. Basically solves the problem of every tool being a different length and you want it to go to 0. G43 makes up that envelope difference. G49 cancels it. We have not used that in the class, so if you have an extra G code at the end of your program and you're wondering what it is, it's probably a G59 or a G49. We haven't used dwell. That's G4 with a P value is usually in seconds or milliseconds. Sometimes you might want the machine to wait for a second. Sometimes at the bottom of the hole, if there's so much tool pressure, you might give it a quick dwell for it to allow the cutter to cut the rest of the metal out of the bottom of the hole. Another time I've used a dwell is if I've got chips that are needing to be for the coolant to blast it off the end of the tool. Sometimes I'll put a dwell cycle in there or G4 It's not a cycle. It's just a G4 to give it an extra couple seconds to blast those chips off the end of the tool. Try not to use dwell because it's a production delay. Okay, G91, G28, Z0 is a rapid to Z0. Did we use dwell on the counterboards for the spring housing? I don't remember. It's optional. Normally, again, I don't use dwell because the tool will tend to rub. If a tool is rubbing, it makes it dull more rapidly. The other way to return to machine 0 is this G53 command. Again, we just leave the G49 out. It's almost getting to be kind of an obsolete code because I don't think you really need to use it at this point. All right, circular pocket milling is something that I would need to review because I don't use it that much. So these are your different values. I would probably keep this handy because you will need to kind of refer to it unless you, unlike me, have the circle pocket milling totally memorized. But we can kind of go through these examples together. So we're calling up the tool number and the tool change. We're positioning the X and Y to the center of the circular pocket, turning the spindle on at 1900, and we're G43 within 100 thousandths of the part, which is pretty standard operating procedure. So we're telling it at this point G13 Z minus 0.375, I 0.5, and D15. So this code also turns on cutter radius compensation. G13, I think G12. Yeah, G12 is clockwise. So again, if you're milling a boss pocket, then sorry, my mouse wheel is not being real super steady here. Go back to using my arrows. If you're milling a boss to mill climb milling, you would use G12. If you're milling a pocket, you would use, of course, I guess circular pocket milling is just for pockets, not for bosses. So forget that I said that. But so rarely would you use G12 because G12 will be conventional milling, and you want to use, as it says here, G42 is always conventional milling. G41 is always climb milling. So the G13 is basically invoking the circular pocket milling cycle. The I is going to, best thing to do is just look at this example because rather than reading all that, it spells it all out right here. If you use this line of code, it's going to mill the entire pocket 375 deep. The I is the radius of the cutter. D15, notice the D15 has to match the T15. All right, it's just like calling up cutter radius compensation, except it's circle pocket milling. Bad thing about this is this thing's going to plunge into the part at 12 inches a minute, and then it's going to just move over and cut this pocket all in one swipe. So if you don't have a center cutting end mill, it's going to cause you problems. The end mill is going to get buried into the workpiece. Now in this example, this example here, these two examples are pretty much all you're going to need to do the circle pocket milling for these three examples. on the final. So in this example, notice all this stuff is the same. It's all the same. So this one feeds Z down into the part. Notice they're feeding it in slower because sometimes you want to plunge at a different speed than your feed rate. And so this is telling it to pretty much do the same thing, except it separates the initial Z move out of the line. So you don't have to tell it the Z move in this line. The reason you would do that is if you wanted a different feed rate than the 10 inches. So this is still going to cut the and honestly, this isn't a whole lot different than the way I program with a G3. It just moves it over for you. Just moves it over for you and then cuts the circle. And I think it moves it back. So there's some advantages to it. The main disadvantage to me is having to remember the rules about it. You can only do this on a Haas. So the problem is, if you had 3 different machine tools in your shop and only one of them was a Haas, you can only run this code on one machine. So I'm more in the camp of trying to, make everything more. But Haas really loves its circle toolpath, so it's on the test. Let's see here. So G43, all this is the same. So this is a 3-inch diameter with so this spells out your I, K, and Q. It's way easier than trying to read it and figure out what it's doing. So your Z is your Z depth, final depth. I, 0.3, is your first circle. Your K, 1.5, is the distance from the center of the circle radius to the outside. Notice they have a 3-inch diameter pocket, so the K is 0.15. I mean, your I value could be many things. It doesn't have to be. So, and then your Q value is the step over. So this would be handy, like whereas the example before is just going to mill kind of an O-ring pocket, whereas this will clear out the whole pocket. And it looks like it steps over gradually. Again, I don't have a lot of experience with this, but this is your sort of your cheat sheet for the final. And then finally, feeding down with the Z-axis before the G13 line. There may be one more because it seems like there's one with this with an incremental move. There's like 4 levels. I can't tell you which one's on the final because I don't know. This is an example of a 4-inch diameter, 1.5-inch deep circular pocket. So the main difference here is difference between this cycle and this cycle is they go G91 and the G13. The I, let's see, 0.325, K 0.2. Oh, it's a 4-inch diameter. So the I is sort of not super relevant. It's just the first circle as it loops into basically going to arc into the bigger circle. Look at the I here, I 0.3. The K, again, is the radius. The Q is a step over. If we apply that same formula to this, and it's kind of a drag because it's on down. So we have the I-325 is the first loop. K 2 inches is the center of the circle from where the X and Y is sitting. With a step over of 300 thousandths, D value again matches the H value, and the L4 says, hey, loop this 4 times. So 3.375 times 4, okay, 0.375 times 4 is 1.5. So anytime you see an L at the end of the line, it's going to loop that line 4 times. So whether it's in a drill cycle or a sub-program call out, it's going to loop it. So those are the 3 or 4 main different robo drills want tool change without G4. Oh, really? I believe that. So yeah, picky machine tools. So you'll run into different scenarios, and it's one thing you'll always find yourself doing is troubleshooting, because there's always problems when you're cutting metal. It could be software, it could be tool deflection, it could be breaking drills. We had a problem today where our Heidenhain, we're like making these stringy chips and everything, which wasn't a big deal when we were doing it on the big Kia mill, because they would just blow the chips off between each hole. Well, it's not so easy on the Heidenhain because the weather's not so great in there because of all the coolant and everything that's pouring down the side of the interior of the machine. And then the guy's got to climb up there, stop the machine, open this 5-foot tall door, and then crawl in there and get the chips off the tap. So we started using a tapping cycle that has a retract, and he's still kind of tinkering with it, trying to get it to work right. It's kind of a pain. All right, moving right along. You're free to use your homework for study guides and things during the final. Open book, open source. Okay, so circular plane selection. You're not going to have to worry about that. It's a good thing to know. One thing you want to be real careful about is if you go to a different work plane, to say you're cutting a circle in ZX, and that would be G18. You want to make darn sure and go back to G17. I had a crash with that the other day because for some reason Mastercam will happily put it in G18 mode, but it won't put it back in G17 mode. So as much code as we spit out, I don't sit there and analyze every single line, But I do rely on the machinist to try to catch some of those, and I can tell you when they don't, they blame me because bad program, Like, well, you should have caught it, man. Standing there running it, right? Okay, so this is some examples of that. Beep. It's important. We've already talked about cutter comp. I think it's way easier to remember an external feature or climb cutting is clockwise or cutter comp left. And then you don't have to worry about what the other one is. Okay, here's that page 61 that Joe was pointing out. This is a really good place to study your radii creation because, well, it gives you the code right here. But actually, with this one, with cutter radius composition, they're just pointing out with these question marks a well-known, let me blow this up a little bit, a well-known deal. We had that one class about the triangles, which I'm not really good at explaining, but you have to really trig all this out when you're not using cutter comps. That's why with the style of programming that we're doing, we program the part path. It saves a lot of time. I will say there's a lot to be said for programming the cutter path because some machines, particularly live tooling lathes, the further you deviate from the actual geometry of what the cutter is doing, the more it has a tendency to make mistakes or overcut or do things wrong. So when possible, it's a good idea to program the cutter path. But manually programming like what we're doing, we're going to definitely, because it's an option really. What the difference is what is your D value. So if you're programming the cutter path with a full size cutter, when you call out G41 D1, your D value will actually be 0 if you're programming the cutter path. So they call that wear programming. So as the cutter wears, and say it starts cutting 2/1000ths big, you would put minus 0.002 if the machine's set up for diameter into the offset registry. Whereas our style of programming, we want it to look at the thing and say, well, we're programmed to the left of the part, but the part is right here. So when we call up our D value, we put our cutter diameter into the offset registry. So just because we're doing it this way here doesn't mean that you would be doing it that way at the shop that you work at. There are different ways of doing it, and 99% of the time, if they're using CAM software like Mastercam or SurfCam or Esprit, whatever it's called, they will be programming the cutter path because it's a more accurate tool path, all in all. But it's just like pushing the post button. You don't have to do all the calculations for the contours. So let's just review this contour real quick. We're moving along pretty good. We still got sub-programs, some drill cycles. I wanted to review the R points, things like that. And if you can kind of have a good comprehension of what we've kind of gone over with the programming up to this point, you can make a lot of stuff on the mill. A lot of stuff. So let's just have a look here. First thing I'm going to do is say, okay, X and Y0 are here. The center of the part. You got 4 inches, 2 inches typical. So that makes this super easy to kind of look at. If you're struggling with radiuses, this is your example, or contours. This would be the example to study. Think of each one of these points on the geometry as a point. You could even go through and draw a little circle around each point. Their points are from the center of the cutter, but we're not programming that way. We're programming the exact geometry. So we're going to wrap it down to our start point. So it's X minus and Y minus. So we know we're going this way because both are minus from 0. And cutter diameter is 1/2 inch. So the radius would be 1/4 inch or 250. And we're minus 2.350 in X. So we're 100,000ths away from the X. And we are Y minus 2 inches because 0 is actually here. So we're Y minus 2, X minus 2.350, which has us off the part, but right on the X, or right on the Y. Sorry. So we're going to drop down to G41 into X minus 2 inches. So we're going to have this G41 here. It's going to cut right into the part. It's going to actually overcut and gouge the part. But since G41's there, it's going to say, oh, I'm going to disappear. Kind of like on the cutter witness protection program when you turn on G41. I'm going to use that again. So that's just putting it right here. Let's see, X minus 2 inches, Y minus 2 inches. So it's right on the corner. And we're going to G41. We're going to feed up to Y 1.750. So here's where the cutter cutting the radius comes into play. It's 4 inches divided by 2 is 2 inches. Now I've got a piano player upstairs. minus the radius, because it's got to be on the center of the cutter. Okay, so if the radius is 250, we are at 1.750 right here because it's 2 inches minus the radius. If you're programming the exact geometry, you don't have to worry about anything else. So it's going to be a G2, which is a circular interpolation clockwise. And we're going to feed to the exact points. X minus 1.750, because all it is from here to here is 2 inches, minus that radius, 1/4 inch, would be X minus 1.750. It's going to be Y.2 because we are on the far side of the geometry, which is right here. And you cannot cut a circle without an R value. You won't have to know this for the final, I don't think, but all your R's are always a plus value unless you're cutting a circle bigger than 180 degrees. So there you go. If I had a 179.9 degree arc for some reason, I guess it would be from here to here, almost 180. It would still be an R plus. But the second I go 180 or more, it turns into an R minus. That way the control knows which side of the sphere you're on. So always remember, go back to G1 after your R value. It's going to feed over to 1.5. And why is it 1.5? Because this is 0, this is 2 inches, minus the 1/2 inch for the radius, puts us at 1.5 at this point. And then again, it's going to be a G2 because we're going clockwise. And notice they're doing all this in absolute, which I think the finals like that too. It's all in absolute. X 2 inches to this far side, Y 1.5 with an R value of 0.5. Now, if this was in G91, you would say it would still be from here to here, because not from here to here, because you still got your comps turned on. It would be G2, G91, X plus 0.5, Y minus 0.5, R 0.5. So that would cut the same arc. Sometimes I like doing circles in G91 anyway, because that way I don't have to really think about where it is from part center. So then it just feeds down to the Y minus 1 or Y minus 1 inch, this exact point. And we're feeding down again to this exact point, X 1.250 and Y 0. Or where am I here? G2, G1, Y minus 1 inch. Oh, I forgot that my 0 was right here. So then you had to calculate, okay, what's 1.250 minus 2 inches? So that's where they're getting the X minus 0.750. And it's minus because your 0 is actually right here. So from this 0 to this point is minus direction and 750 thousandths and Y minus 2. And it just basically just feeds over. So if this is 2 inches from here to here, you got a 1/4 inch radius, it's going to be X minus 1.750, because pretty much, 2 inches minus 250 is 1.750. And then it cuts it, cuts this last radius. 2 inches, and then Y minus 1.750, because same deal, from here to there is 2 inches, minus the 1/4 inch is the end point of that arc. So I think that will be the extent of the knowledge that's required to cut the contour on the final. So if you understand that, you're in good shape. If not, maybe just kind of review it as best you can. If you still have questions about it, you can text me or call me. I want to make sure you guys understand it. All right. Any questions? Nope. Not visibly, anyway. I feel like I lost a few people. Let's see who's all here. Oh, we got quite a few here tonight. Welcome to Sim 122. This is actually our last this is our last online class. While everybody's here, I feel like some of you may drop out. I wanted to talk a little bit about the lab opportunities that are coming up towards, see, it won't be next week, but it'll be the week after. And these are the dates and times. And I'm only allowed to have 9 people. So if I have less than 9 people from both classes that I teach, you'll be more than welcome to come down for both classes. And we'll know that Thursday, the 14th. I'm going to post this letter under announcements, and it'll kind of give you an idea of there we'll be requiring students, faculty, and staff to wear masks or face coverings and practice social distancing while on campus. If you do not have a mask or face covering of your own, please let me know and I will arrange for one to be provided for you when you arrive. There's only going to be a single point of entry at the school, so I'm thinking that's the opposite side of the school that we usually go in on. So for me, this is kind of a one-time opportunity. There will be no expectations point-wise with this. I feel like you guys did get slighted. Of course, it's no one's fault, but you got slighted with some lab time. And if you'd like to come in and get some more hands-on time with the machine tool, send me an email tonight. I'm going to post this so you can read over it after class and make a decision one way or another. I just need to know how many. I have to submit anybody whose name who wants to participate in that lab, because it's just the rule. They're running a really tight ship on that. So if you think you may want to but aren't really sure, you can let me know that too, and I'll put you down as being there. And if for some reason run out of seats, then I'll probably contact you and say, hey, do you really want to do this? Or so anyway, that's kind of the gist of that. Any questions about it after I post the letter? I kind of changed the letter a little bit. Can you cut a 3 serve? I'm not real. Joe asked if you can cut a 360 circle using an R. I think you can. I've never tried it because I always use the I and J. So that would be a good reason for you to go down to the lab and and try that. But for the most part, I just use I and J to cut full circles. So this is kind of explaining more of why, some different options with milling contours. So third compensation exercise. Some of y'all still need to turn in homework. I'm not 100% sure of. The reason I asked you, as you said a few minutes ago, that we would use. Yeah, you won't be. Well, you'll use I and J with the circle pocket milling, as it's used in the circle pocket milling, but you won't use you won't need to use I or J to cut the radiuses on the contour. Does that make sense? Like for the final, yeah, okay. Yeah, for the final, when you're cutting a simple radius like this, you won't have to use I and J. So let's see, gonna go on. Didn't do thread milling. Thread milling is not on the final. We were going to do a little bit of thread milling. It wasn't going to really be thread milling, though. We were going to use a thread milling tool to cut the grip wheels. And I did have the bright idea to do a helical motion on the grip wheels going both ways. Keep spitting on my computer. That's why we're supposed to wear masks. And try to effectively cut a knurl by doing helical motion going one way and then the opposite way. But it turned out that doesn't work because they only intersect in one spot on the wheel. So I spent a whole class on that. Sometimes you just gotta experiment with things. Okay, so your R plane, most of you guys that turned in your homework for the R plane did really well with that. Just a little reminder that with your R plane, with your G98 and G99, this is a super good example of where that G98 would have to go actually between hole 3 and hole 4. And most of you picked up on that pretty good in the homework. One thing I did see a little bit of was the tendency to want to turn off your CAN cycle right here with a G0 and then add your CAN cycles back in before your G98. This is not necessary. Drill cycles are really forgiving in that you only need to change the values in the CAN cycle that are different to the next hole. So in other words, like in this example, you've got a different Z, you got a different R, and you're going to G99 from G98, but notice we're still in G83, so it assumes that G83 is the same. It assumes that Q.2 is the same, and it assumes that F8, 8.0 or 8 point is the same. So that makes sense. You just need to change the values that are different until it reads G0 and cancels out the CAN cycle. So when will we know our grade? You will know your grade after I get everybody's final graded. I think that they are allowing a couple extra weeks in the semester, and I didn't want to do that because there's been a fair amount of effort just moving to online classes and getting everybody kind of back reeled in after the meltdown. And but so the points that are out there right now is it, and I'm just going to base, I haven't figured out what that is yet. I can guarantee you it'll be super fair. I wasn't sure how far we'd get with the programs and things because this is a really unique situation. And the syllabus, it does talk about how every class is different and the points can vary from class to class. And this has been about the most different class semester I've ever dealt with. So I've really kind of been winging it. I can assure you that if you've been doing your work and turning it in, you're going to be happy with your grade. I'm not going to post grades until the actual end of the semester, but I will post to you guys in an announcement what the total points are going to be. And if you're not happy with your grade at that point, it might mean that you need to turn in an assignment or something. And so I think there's going to be a good couple weeks after the class. I'm not, encouraging people not to get their work done, but there's going to be a good couple weeks after the end of the semester where you will actually have time to backfill and get some of your stuff turned in if you haven't got it done. So I feel like there's going to be plenty of opportunity. We've, kind of scaled back expectations somewhat with that, turning in projects and things. And for the most part, I'm not really rigid on grading projects. I just like to see people working on the machines, taking offsets, getting their hands on the machine. And if you were cranking out perfect parts, you wouldn't need to take the class, right? So that said, you will know your grade probably. I'll try to get everything squared away, the weekend, like not this weekend, but next weekend. By Monday, you'll have an idea where you're standing in the class. I like to go ahead and get things done so that, you're not left hanging. I'm not left with responsibilities. and I'm just not sure how the whole point schedule is going to shake out. I've also had times where I've curved the curved. I was getting in trouble for saying curb because my wife hates it. It's not curb. It's curve. Where I've curved the point schedule depending on what we're actually able to get done. I might have one student who's like 500 points ahead of everybody or something, but I take all those things into consideration, and for the most part, it's going to be fairly static. It's going to be the homework, it's going to be the final, and there's a few things that were left undone, like some people got parts of projects done that other people didn't, and some of that's just going to have to be a wash because you can't obviously hold you guys responsible for parts of projects that we're going to maybe get done in a different class. So you should be pretty good with your drill cycles. G81, G73, G83, G84. This is a really great example. Like if you wanted to study drill cycles, I recommend some of these diagrams that we're looking at. If you want to write down some of the page numbers, that it's going to picture's worth 1,000 words. So this, page 74 on down really describes, here's your G81. This is going to be your spot drill. One other thing before I do forget is speeds and feeds are going to be important. So you'll need to be able to, if you are given a tool diameter and you're given a surface feet and a chip load, you should be able to calculate what your RPM is and what your inches per minute is. So let's do an example here. Say we've got a 1/2 inch end mill at 1,000 RPM, and we want to run a chip and a 4-flute end mill, 1/2 inch 4-flute end mill, and we want it to run not 1,000 RPM. We want it to run 100 surface feet. We'll keep it simple. 1/2 inch 4-flute end mill, 100 surface feet at 3 thousandths per reb per flute. Okay, so remember the 3.820. That's basically pi divided by 12. 12. No, I always do that backwards. 12 divided by pi. You're basically putting pi into feet by doing this. So surface feet, 12 divided by pi. We round it up to 3.820 because it's easier. So it'll be pi, the 3.820 times your desired surface feet. And this is in the book, too. Times your surface feet would be 100 equals that. So we got 382. That ain't right. Yeah, it would divided by 0.5, which is the diameter of your cutter. You're going to run it at 764 RPM. So the same token, find out what my inches are. You always find your RPM first because inches per reb per flute will be 764 RPM times 3 thousandths per reb, 0.003, enter. See, now you've got 4 flutes. Okay, so you got to multiply that times 4. So that's going to be 9.16 or 9.1 inches a minute. Or actually 9.2 if you want to round it up. So is that, anybody got any questions about that? That is the main speeds and feeds calculation you're going to need to know. I usually have it memorized how to figure both ways, but you don't need to do that. Like if I know my RPM, I have the inverse function for figuring out what my surface feet is, because when I was doing setups and I would always make sure my surface feet were good to go. Okay, so I've had people use the spot drill cycle. I'm not real familiar with that one, so I don't use it. I think the difference is Rapid position, can cycle, spot drill. Should tell what it does. G82 is pretty much the same as G81. I don't really know what the difference is, and I don't want to spend a lot of time on it. So you can use either one, unless it tells you different. Be sure and read the instructions. Peephole. So that's something that's a good thing to remember. That's when we have a full retract on our drill bit. And there is, it looks like they say that's a G83. So these arrows kind of represent the tool movement. It's going to do a full retract, which looks kind of wonky. And then pretty much that, and then this review of sub-programs. I think that's about it. So this tapping cycle would be another thing that you may have to calculate the speeds and feeds for the tap. So remember, the tapping cycle, it's always 1 divided by the threads per inch times your RPM will equal your feed rate. So if I got a 1024 tap, because a tap, the speeds and feeds, RPM and feed rate has to be synchronized. So if I have a 1024 tap, 24 is the threads per inch, 1 divided by 24 is that. Simply times, say I want to run at 300 RPM, it's going to be 12.5 on the feed rate. I just got lucky that it came out that exact. I do try to get it to where it's down to 1 digit, but you won't have to worry about that on the final, so it's just another thing. Just the formula. We won't do reverse tapping. All pretty straightforward stuff we've been programming and doing, with the exception of pocket milling. Bore in, bore out, kind of like wax on, wax off. This is a good cycle because, yeah, we won't go into it. A lot of machine tools have different hand cycles that do different things. I try to stick with the big 4 that you'll run into. Not doing any of this. See all these bore cycles, so there's options. Hand cycle exercise number 2. Wonder where it gets into sub-programs. High speed peck. So this is more of that shallow peck cycle where it doesn't fully retract every time. I find these diagrams to be kind of confusing, actually. I, J, and K. We're not going to do any of that. Remember, I kind of explained the IJK thing. The first peck can be deeper, and then each peck gets subsequently shorter with the J, and then K is the minimal amount, which is great, but it only works on Haws. 76. Back bore. Bolt hole patterns, not doing any of that. So yeah, Haws has some pretty cool features that it will do. Did I skip some programs? We're not doing can cycle exercise number 3. Because for one thing, we're out of time, but it uses a lot of this IJK stuff and it's bolt circles and things that are really super pertinent to Haws. Subroutines. Okay. If you remember right, the subroutine is where we have duplicate data that we could run for each tool, whether it's the same group of holes or if it's a contour that's the same that we're going to run around 3 or 4 times. the subroutine is going to save you a lot of headaches because, for one thing, if you're going through with a drill, center drill, and a tap, once you're in your subroutine, if you watched it run once, you know that you don't have to worry about sending it to the wrong hole. There's an example of, it's pretty much the same example they use for other things, which is kind of nice. That way you're used to seeing it. But they're showing you how a subroutine can save you from calling all these holes out over and over again. So it's going to, on page 106 here, it's going to be a really good example of a subroutine. Excuse me. Anything that's different about the tool or the tool path has to be out in the main program. So if you look at this data, you got 3 different tools. So obviously this line's the same on all 3 tools, but you can't put it in the subroutine because you always want to position X and Y before you move Z. And so each tool has a different RPM. Each tool has a different H value. Other than that, all that information could go in the subroutine, but you just can't because this is different. Your feed rates are different. Now, you can pull little tricks and things, but if you follow this format, you'll do fine on the final. So basically, they're positioning the first hole, the program all the way up to the first hole, drilling the first hole, or tapping the first hole, or doing all the features on that first hole. Then they call out the subroutine, but there's nothing else after that. And the reason for that is everything after that is the same for each tool. For example, E53, all this, 49Z0, this is all going to be the same for each tool. So by putting it in the subroutine, you save 6 lines of code. So the rules are simple. I'm not sure if the final has a local subroutine or a remote, but I mean, I'll accept either one because we didn't do a lot with subroutines. But the difference is if you have a subprogram that is its own separate program in the program library, it's going to be an M98. If you have a program that is nested at the end of after your M30, it's going to be an M97. So this would be, for both, returning back to the main program is M99. So that's going to loop back in. And then this is the example with the local. So page 107, 108 will be your subroutine cheat sheets or program assist. We're not gonna mess with general purpose. That's as far as we go. So yeah, so this is just going back to the same. This is the subroutine after the M. So here's your M30. Notice that they're calling out P10 here, but there's an N10 here. N10 is the name of the subroutine. You cannot use 2-letter O's in the same program. So the way Haas does this, gets around that, is by giving it an N value instead of an O. So anybody have any questions? Any questions at all? Is there anything anybody would like to review some more? Well, if you think of any questions during the week, um, or if want, I think Joe was asking about copies of his homework. I said, yeah, they're in my deleted files. The reason I was doing that was because that way I'd know I'd already looked at it. But I think I can retrieve those and get them back to you if you've lost them or need to know anything else. And so when I sent out the invite, the announcement for the lab time here in 2 weeks. So it won't be next week. It'll be a week after that. Same class time will be from 5 to 10 at night or 9:50. Let me know if you're interested in that because I need to get your name to Mike Klein so that he knows how many people to expect. And if I have less than 9 people between both classes, again, you can come down Saturday as well. But we'll just have to wait and see on that a little bit. There's no mandate to do that or anything like that. It's just if you want some more hands-on time, because it is more of a hands-on class than it has been. So, but also, I wouldn't talk about it too loudly. But next semester, I'm teaching the first 8 weeks. I'll be down there if my classes go. I'll be down there Thursday because the lathe class is going to run. They're trying to get everything done the first 8 weeks. So the lathe class is going to run Thursday and Friday night. You're welcome to come in and work on the CNC mills then if you like. And it's kind of one of those better to seek forgiveness and ask permission things. But then I've also got an advanced mill class that's going to run for 10 weeks from 8 a.m. to 4:30 on Saturday. So it's going to be brutal. But I will, if you were in this class or the advanced lathe class and didn't get your machine time in, I'm all about you coming down there and tinkering around with the machines. But just let me know if you're going to do that. So I'll put the information up about the lab time. If anybody doesn't have any more questions, I guess we can be done kind of early and just give you guys time to study. I didn't want to put any more points out there. And after the final next week, I will definitely, probably by Sunday night, have something posted for what the total points for the class are, and then you can get on Blackboard and see what your points are. And then do the math because it's 90% for an A, 80% for a B. It's all in the syllabus. So if no one else has any questions, I guess you guys are good to go.